Okay, so here we go with the review of the homework on Solutions 2 Concentration Conundrum. And this is just going over the basic formulas and how to actually use each of the different types of concentration terms that we have. Case in point, we have molarity, okay, with the R, and that's the big M, that's moles of solute over liter of solution. And I'm using the key to go over this. And we have molality, which is the little L here, and that, of course, is moles of solute over kilogram of solvent. A little different. Molarity is moles of solute over liter of solution. Molality is moles of solute over kilogram of solvent. Let's talk about those differences a little bit, but I didn't get a chance to do today in class. Okay. First and foremost, they're very similar. Okay, and they're similar in that we're using the moles, how many particles of solute. How they differ is what the denominator is using. Here we're using liter of solution. This is using a volume unit, okay? And here we're using a mass unit. Okay, now why do we differ? Why do we even have molality? Because we universally use molarity a lot, okay, in different types of solution, types of questions, equilibrium, acid and base, redox, so forth. Molality raises its head a little bit in this area of colligative properties where we're adding particles to a solution, because one of the effects, as we're going to see, is freezing point depression and boiling point elevation. We're going to have changes of temperature, okay, associated, okay, or we're going to have, I should say, we're going to have temperatures that are going to be high and low as we evaluate boiling points and as we evaluate freezing points. Okay, and this analysis of freezing points and boiling points, as we deal with a range of temperatures, we know that the concentration molarity will not stay constant at different temperatures. Volumes, as you know, are basically very sensitive to temperature. If temperature goes up, we know the volume of a liquid is also going to go up a little bit. Not as much as a gas, but it does go up. So liquids do expand. That's why warm water is less dense than cold water. Cold water volumes are, in fact, going to be more dense. Therefore, when the solution gets colder, the molarity, the liter, or the volume of the solution goes down, and the molarity actually goes up. Okay? That's why they always say you should actually buy gas in the morning, because when you buy gas in the morning, it's colder in the tank. If it's colder in the tank, all right, you're actually getting a higher, more dense gasoline than you would during the day. So you're getting more product, okay, or more molarity if you want to think of it that way. Although it's not mixed with something, it's a pure compound. But you get the point. Colder things, okay, have a larger density. They're packed tighter, so therefore their volumes are less. And since the gasoline is measured by volume, you're getting more gas out per gallon at the pump if the gas is colder. So you kind of knew that. So molarity is used where temperatures are staying absolutely constant. They're at room temperature. There's not much changes going on. Molality is when we're talking about a boiling temperature, a freezing point, very cold changes. We know that mass is independent of temperature. So that's why molality with the L is used. Okay, now these are two basic ways how we make solutions. A molar solution is made using something called a volumetric flask. It's a long flask with a known volume, and it has a mark. It's very expensive. That mark, let's say, could be a 1 liter mark. And if I was to make a 1 molar solution of, let's say, salt, the table salt, NaCl, I would need a mole of it, and we know that 23 plus 35 is 58 grams. So I know that 58 grams of table salt is 1 mole. Okay, so how would I make a 1 molar solution? Well, one way is I can fill this up all the way to the 1 liter mark and then add the 58 grams. And we know that by this Archimedes principle that this line would actually raise up and be above 1 liter. And that would not be a molar solution. What we do is we would put the 58 grams in here first, pre-dissolve it with a known amount of water, and then add the water till it reaches this line. That's how we make a 1 molar solution. Okay? So, and we have to be very careful not to fill past this point. Molar solutions are harder to make because of that. Now, a 1 molal solution, well, because I'm dealing with, okay, kilograms of solvent, the density of water is about 1. I know that I need 1,000 grams of water. Density of water is 1 gram per milliliter. So therefore, okay, 1,000 grams is 1,000 milliliters, which of course is 1 liter. All right, so I'd start with a liter. So if I was to do a molal, uh, solution, same flask, my drawing is terrible. What I'd start with is exactly what? Start exactly with a liter of water, and then I would add my 58 grams after. Could care less if it over what? If it over spills or overpasses the 1 liter mark. Who cares? I have 1,000 milliliters or a liter of water with 58 grams. Could care less what that mark is as long as I know I'm dealing with 1 liter first. So molal solutions are easier to make. Okay, hey, take a liter of water, measure that, and then add the stuff to it. Who cares? 1 molar solutions, I have to pre-dissolve it somehow and make sure that I add water to it till I get to the mark. I can't do it this way for molal solutions because, as you can see, you won't have a liter of solution anymore. So these are easier to make, okay, than molar solutions. And they have some connections, okay. In the problem that we did, or you have done, which is laid out here, we got 0.14 molar and we got 0.119 molal. And these are very similar numbers because the concentrations are very low. Now, why are they approximating each other? Well, if you think about the way that they're made, okay, if I add a little bit of solute particles on top of this 1 liter mark, will it change that 1 liter mark that much? No. And of course, if I add a liter of water and just a little bit of solute particles, okay, these guys should be close because there's not going to be much displacement above the 1 liter mark. I'll say that again. I'm going to make a 1 molal solution here and a 1, let's make a small number, I don't know, 0.01 molal solution here and a 0.1 little m solution called molal here. Okay, so 0.01. Now if I'm doing that, I need 100th of this, right? So 0.58. So I take 0.58 grams and add it to this. Essentially, it's almost all water. Okay, so I would add some first and dissolve. Then I would take 0.01 moles, 0.58 grams, and I would add it on top of the 1 liter mark. And I bet it barely moves. If it does, it moves a little bit. And as you can see, this a little bit to the top would approximate exactly doing it this way. Now, as you add higher amounts of salt, there's going to be a greater displacement, and these values will differ from each other. Okay? So you should know they approximate each other in dilute solutions because of the displacement that occurs on top of the 1 liter. That displacement will approximate exactly the 1 molar solution when this value you're adding to the 1 liter is very small. Okay? Now, in my problem that I outlined for you here, okay, and let's get rid of the stuff that I've talked about to make things a lot easier to look at, okay, I came up independently with these values, 1.6 liters over the moles, 1.4, and then of course this is pretty simple stuff. I converted my grams given to moles using the molecular mass, and I plugged that back in to the liters that were given. Easy work here. Number 2, there was some more work involved because I had to find the what? The kilograms. The moles of the solution I already had from this problem, and what am I doing? I'm dancing around here. Hold on. So here, I need to find the mass of my, not solution, mass of my solvent. Okay? So I took my 1.6 liters, converted to milliliters, and I used the density formula, okay, to convert my volume into mass. Then I convert it to kilograms. Now this was kilograms of solution. I knew that there was 23.3 grams of the solute particles trying to be dissolved. So I subtracted that to get my water. And that's the grams of my water or solvent. And of course, that is what's going into here. Plug it in and you get the value. Because this is a dilute solution, these two numbers approximated each other. Okay. What's the mole fraction? Okay, it's just comparison of moles. So as I say, we have the moles of KNO3 already, 0.23 moles. Why? Because we converted the grams given to the problem. And we already have the mass of the water that I just calculated from above. So now I'm going to convert that to moles. To do a mole fraction, it's part over total. We're doing a mole fraction of what? KNO3. It's written just like this. The fraction of KNO3. So KNO3 moles goes up top. Okay. And the total moles, and this is why people they'll put the moles of the water on the bottom and move on. Be careful. A fraction is part over total. So you got to add both of these moles to get the total moles of the solution. Okay, not hard math, except with me sometimes. But you just have to be aware of what you're doing. Okay, and of course there's your mole fraction. Notice the mole fraction is tiny. Why? Because it's dilute, which means your molality and molarity should approximate each other. Okay? What's the mole fraction of the water? Well, it's easy. If you know the mole fraction of your solute, the mole fraction of the water is 1 minus that. If you want to figure it out mathematically, you can, but you can certainly subtract it from 1. Okay, this is pretty simple stuff. You need to go through this. What's the percent by mass of a solute? Percent by mass, okay, is a part over total times 100. But this is the total mass of the solution if you're doing a percentage or a fraction. Okay, so I needed the total mass of my solution. We got this by using the what? The total volume. Going through density, we found the total mass. Okay. What is the part per million? Well, part per million is the same thing. It's part over total that we're talking about. Now again, total mass of solution. This is mass. Instead of timesing it by 100, we're timesing it by 1,000,000. If it was part per billion, you change that number. So it's so simple. So I take this, which is the part of my KNO3, over the total mass of the solution, because it's based on mass, and I times it by 1,000,000. So very simple stuff there. Number 7 is really meant for honors chemistry because we need to have a table H, or I'm sorry, table G, a solubility curve table to see if it's on the line, below the line, for a particular temperature and pressure. So this is not part of AP Chem. So you can just scratch that. Okay. Now, number 8, backside. As we go through this, a solution of hydrochloric acid contains 36% hydrochloric percent by mass. What does that mean? That means 36 grams of hydrochloric acid molecules in 100 grams of water. I'm sorry, 100 grams of solution. Remember, it's total solution, percentage and fractions using mass, total mass. So this is over 100 grams of solution, which means 100 minus 36, 64 grams of water. They want the mole fraction. Convert your grams to moles. Don't have to hold your hand there, and that's what we get. We get those values. To do the fraction, we get total moles in the bottom. And what am I asking for? Mole fraction. Be careful. Mole fraction of HCl. So HCl's value goes up top, and we get a mole fraction, which is much bigger than the one we had above there. Okay. Calculate the molality. Now careful. Molarity, molality. L. Okay, so M is moles of solute, kilogram of solution, and molality is, well, the moles that we have, which is, again, for HCl. We figured from above it was 1 mole, and of course, it's kilograms of solvent. Our solvent is water. So from the above question, 64 grams is converted to kilograms, and we get 15.6 mole out. Again, pretty significant mole fraction, okay? except I think this is incorrect. There's no way this is 2.19. Okay. Yeah, that's definitely wrong. You think about it because it's a fraction. I'm off by a decimal place here. Sorry. Okay. I continue to have some problems with this math today. Any case, so this is 0.219. That's very significant. 2.19, hey, I don't know how do you explain that as a fraction. I have one pizza, but there's two of them in there. I'm not sure. But yeah, it's 0.2. So what that means is 21.9% of all the moles is due to hydrochloric acid. That's pretty significant. So 0.219. Okay. All right, I'm getting there. Moving on. Number 9, given the density of the solution and given the grams of each, calculate the molality and molarity. Okay, well, this is good for you to go through. Okay, write down the formula. Be aware what you're doing, not hard. Okay, and I have 5 grams of toluene. I have 225 grams. The only problem people have is, hey, Mr. Grazi, which one's the solvent? Which one's the solute? Okay, these are both miscible in each other, but the one in higher amounts is your solvent. Okay, so the benzene, I convert to moles. Okay, and the reason why is I'm going to need them in different parts. Molarity, let's do molality first. Okay, moles of solute, kilogram of solvent. Okay, so I'm going to take my grams of my solvent and convert to kilograms. And I need my moles of my solute, which is the smaller quantity. So again, if you're given two values of two liquids, who's the solvent, who's the solute, it's the one in greater quantity we call the solvent. And we get 0.24, pretty easy stuff. Molarity, so this is molality, okay, molality, okay, any case, big M, okay, and in any case, molality is this, moles of solute, liter of solution, and I'm going to use the same solute, and now I need liter of solution. So Christmas in July, what did they give me? Well, they gave me just the grams. So what I do is I'm going to add those grams together, 225 plus 5, and that's going to give me a total of 230 moles. Now, why did I do that? Well, once I know my total moles, I can convert the total mass of the solution to the total volume, and you guessed it, using density. I don't know if you really guessed it, I'm just guessing. Okay, so once I have my total volume, again, if you know what this is all about, you know the details and how these equations are used, you can better figure out these little, not so hard intricacies, but these little different things you have to do here. So yeah, you have to add these together to get total solution. And of course, through the density formula, and converting 2 liters, you get your liters. And of course, that goes on the bottom. I don't know why it did that. Sometimes it goes this way and then back this way. All right, and of course I solve for it. And they are going to approximate each other because, well, 5 grams of solute in 225 grams is a dilute solution, so these should be similar. Okay, and that concludes this ditto. And hopefully you went through that and did the problems out and followed my little hints, especially why these do approximate at low levels, and of course why we use molality instead of molarity when we're dealing with temperatures that are in great ranges. Okay.